Welcome to the deep dive. Today, we're taking a deep dive into MIG welding. If you've ever looked at a modern skyscraper or maybe a new car and wondered how all that metal comes together with such incredible strength and speed, well, this deep dive is for you. Our mission is really to cut through any sort of technical fog and deliver the crucial insights on how this widely used industrial process actually works. We'll focus on its clever mechanisms, the essential components, get ready for some truly surprising facts and maybe a few aha moments about this invisible hand behind so much of our built world.
It really is a foundational topic, MIG welding, or gas metal arc welding, GMAW as it's known in the U.S. It's a real workhorse process.
GMAW, right.
Its broad application in, well, everything from automotive manufacturing right through to heavy construction means understanding its core principles is incredibly valuable, especially if you're curious about how things get made at scale.
Okay, fantastic. Let's unpack this process then from the ground up and really try to uncover its ingenious design. So at its most basic level, MIG welding is known for being versatile. Right? It can join thin sheet components, like you mentioned, car bodies, and also really thick sections, things you see in large structural beams. And it works across almost all metallic materials.
Yeah, the central idea is, it sounds simple, but it's incredibly effective. You strike an electric arc, and you maintain it between a continuously fed wire electrode and the piece of metal you're welding, the workpiece.
Okay.
This arc generates intense heat, melting both the tip of that wire and the base metal. They fuse together to form a molten weld pool. And what's really brilliant here is the dual role of that wire. It's not just the source of the arc's heat.
Yeah.
It is the filler material for the joint. It actually becomes part of the new, strong connection.
Right. It's consumed in the process. And the practical setup is pretty clever, too. That wire, it's spooled continuously from a big reel.
Quite large, yeah.
Driven by a motor through a copper contact tube. Now, this tube is vital because it's what delivers the welding current right into the wire.
Exactly.
Then to protect that molten weld pool from, contamination by the air around it,
right.
Oxygen, nitrogen, things that weaken the weld.
Big problem if they get in.
Right. A shielding gas is fed through a nozzle that surrounds the wire. And the welder, or maybe a machine in automated setups, moves this whole gun or torch along the joint line. Right. And that continuous wire feed, that's a major efficiency driver, isn't it? It leads to really high productivity, makes the whole process very economical in industrial settings.
Absolutely. And what's also remarkable is just how scalable this process is in terms of automation. You see it applied across a really wide spectrum of production needs.
Yeah.
So at one end, you've got semi-automatic welding. Here, the wire feed rate and the arc length, they're controlled automatically by the machine. But the human welder is still in charge of the travel speed and, crucially, the precise position of the wire. Then you move up to mechanized welding. Now, all parameters are under automatic control, but an operator can still make real-time manual adjustments during the weld.
Like tweaking things on the fly.
Exactly. Maybe fine-tuning the wire feed speed or the arc voltage, perhaps steering the welding head slightly. And then, for the ultimate in speed and consistency, you have fully automatic setups. Once they start, there's basically no manual intervention needed during the welding at all.
Wow.
The ingenuity really shines in how these different levels cater to everything from, say, a small fabrication shop with a skilled hand welder, right up to a massive, fully automated factory floor assembling huge components.
So, okay, we understand the core process, these different levels of automation. Now, what does this actually mean for the workshop floor or the construction site? What are the kind of the practical benefits and challenges that really define this technique?
Well, to really grasp its versatility, let's maybe pivot to the essential equipment. Because getting this invisible hand working requires several core components all working together in harmony.
Right, the hardware.
Exactly. You need the power source, first off. That could be a traditional transformer rectifier type or maybe one of the more modern compact inverter types.
Later, usually.
Generally, yes. Then there's the power hose assembly. Think of it like an umbilical cord. It contains the liner that guides the wire, the electrical power cable, and the gas hose, all bundled together.
Okay.
Of course, you need the actual torch head assembly and, crucially, the contact tips within it. These wear out, so you need spares. Completing the electrical circuit is the power return cable and clamp. That connects back to the workpiece.
Gotta have that ground.
Absolutely. Then the wire spool itself, typically maybe 15 kilograms, holds the welding wire. And the wire itself can vary, often copper-coated, sometimes uncoated. You also have a power control panel to manage all your settings, voltage, wire speed, that sort of thing. And finally, the wire feed unit. Sometimes it's an external box, sometimes it's integrated right into the power source.
That wire feed system, it really feels like the heart of the operation. And it has some fascinating design details when you look closely. Inside that wire drive assembly, you find these drive rollers. They come in different designs, maybe a plain top roller, a half-grooved bottom one, specifically engineered to grip and feed that wire really precisely.
And those drive rolls are much more critical than they might appear. They come with different groove shapes, like you said. Each one is optimized for a specific wire type. So like a V-groove is common for stiffer steel wires. A U-groove might be used for softer wires, like aluminum stops them from getting squashed. You even get knurled rolls sometimes for when you need a really aggressive positive feed. But here's the kicker, and where a lot of problems can start. The tightness.
The tension.
Exactly. If the drive rolls are too loose, they'll just skid. The wire stalls, no arc, no weld. Simple as that. But if they're too tight, they can actually deform the wire, squash it, which makes it incredibly difficult to push smoothly through the liner downstream. That can lead to frustrating things like arcing right inside the contact tip or excessive wear on the liner and tip.
That sounds like a nightmare to troubleshoot.
It can be.
Right.
And the consequence, if the wire completely stops feeding, by the way, is the arc can burn back up the wire right into the contact tube. Definitely not a good situation for your equipment. Which, raises an important question.
Yeah.
How does the system stay stable with such precise, high-speed feeding needed, especially when that wire is moving so fast?
Yeah, good question. And that brings us to another sort of unsung hero in the system, the liners.
Ah, yes, the liners.
Yeah. These are thin tubes, usually tucked inside the welding gun and the hose assembly. Their whole job is just to guide the wire smoothly from the spool all the way to the contact tip. For steel wires, you'll typically see these close-wound stainless steel liners. They're pretty durable.
Robust, yeah.
But for softer stuff, like aluminum wires, you use Teflon liners. Why Teflon? Well, to minimize friction, basically, and prevent any damage to that soft wire as it zips through.
Makes perfect sense. And this careful feeding system leads us neatly into one of the most fundamental and, frankly, just ingenious principles of MIG-MAG welding, the self-adjusting arc.
Okay, the self-adjusting arc, what's that about?
It's this incredible constant equilibrium. It happens between the arc itself and the wire feed rate. Imagine this. If the arc length momentarily increases, maybe the welder lifts the torch just a tiny bit.
Yeah.
The wire's burn-off rate actually reduces slightly. But because the wire feed rate itself is constant, set by the machine, more wire feeds into the gap. And the original arc length is almost instantly reestablished. It corrects itself. And conversely, if the arc length momentarily shortens, maybe they dip the torch too close, the burn-off rate increases, consuming wire faster, and again, the system rapidly returns to its stable original condition.
So it's constantly fine-tuning itself.
Exactly.
Yeah.
If we connect this to the bigger picture, it's just a prime example of intelligent automation ensuring consistent weld quality. Even with those minor unavoidable fluctuations in human movement or machine travel, it really simplifies the welder's job and dramatically improves weld reliability.
That's really clever. It sort of compensates automatically. And what's truly ingenious here is how it handles even subtle changes, making precision welding far more forgiving, more consistent. Like, think about this. If your welding gun moves just a tiny bit further from the metal, increasing what's called the contact tip to work distance, or CTWD.
The stick out?
Right, the stick out. You might expect the weld to suffer, right? But no, the system dynamically adjusts. The welding current actually decreases in response.
That seems counterintuitive. Why?
Because that longer path for the current through the wire itself before it arcs creates more resistive heating in the wire. It gets hotter just from the electricity passing through it over that extra distance, and that subtly impacts the overall current draw.
Ah, I see. More resistance heating in the wire extension.
Exactly. And conversely, when you reduce the CTWD, bring the tip closer, the welding current increases. It's like the system has its own built-in shock absorber, constantly maintaining optimal performance despite these small variations. That's where it gets really interesting. Like, the system is always working to keep that stable, powerful arc.
That self-regulation is key.
Definitely. So, okay, we've broken down how this process works piece by piece. Let's talk big picture now. Advantages and disadvantages. What makes MIG-MAG so popular?
Well, from a practical standpoint, there's that continuous wire feed we keep mentioning. Massive boost for productivity.
Huge.
We just discussed the automatic self-regulation of the arc length. Incredible consistency. It delivers a high deposition rate, meaning you lay down a lot of weld metal quickly.
Fast welding speeds, which means minimal stop-start locations in a weld bead. That translates to faster work and fewer places where defects might occur. You also get high consumable efficiency. Most of the wire ends up in the weld. And typical heat inputs are in a pretty controlled range, usually 0.1 to 2 kilojoules per millimeter. That helps control distortion.
Important for precision work.
Yeah. And the welder has excellent visibility of the weld pool and the joint line, which really aids control. Plus, there's often little or no post-weld cleaning needed, which saves time and labor. And generally can be used in all welding positions, although some are easier than others.
Sure.
Overall, it offers fantastic process control possibilities and just an exceptionally wide range of applications.
It's true. The advantages are incredibly compelling, especially for high-volume production. But like any engineering solution, it definitely comes with its trade-offs. There are disadvantages to consider.
Okay, let's hear the other side.
Well, for one, you don't have independent control of the filler addition rate separate from the heat input, which can be a limitation for certain very specialized, highly precise applications where you might want that. It can also be surprisingly tricky sometimes to set up the optimum parameters to really minimize spatter levels. That often requires a lot of fine-tuning, trial and error.
Right, those little balls of metal flying off.
Exactly. There's also an inherent risk of lack of fusion, especially when welding thicker materials if your parameters aren't quite right or the joint prep isn't perfect. The equipment itself, with all those moving parts, the feeder, the liner, it requires a high level of maintenance to keep everything functioning smoothly.
More complex than a stick welder.
Oh, definitely. And the initial equipment cost is generally higher compared to simpler processes like manual metal arc, MMA welding, or stick welding. For outdoor or site welding, you absolutely need special precautions, screens, shelters to exclude drafts. Even a gentle breeze can easily disturb that crucial shielding gas and compromise the weld.
Good point.
Joint and part access can sometimes be more challenging too. The MIG-MAG torch is generally bulkier than, say, an MMA electrode holder or a TIG torch. And finally, it generally has less tolerance for base metal contamination, things like rust, oil, paint, compared to processes that use a slag covering to help clean the weld pool. So connecting that to the bigger picture, it really is about understanding these trade-offs. You need to select the absolute right tool for the specific job, weighing that high productivity against these operational considerations.
That makes sense. It's always a balance. Now, let's quickly touch on inspection and safety. These are absolutely critical for any welding operation, right?
Paramount. Absolutely.
For inspection, a basic visual check is always the first step, just making sure the overall welding equipment looks like it's in good, serviceable condition, no obvious damage. But a particularly crucial point, and one that's maybe easily overlooked, is checking all the welder connections for soundness. Electrical connections.
Critically important.
Because any loose connection anywhere in that circuit will create electrical resistance. That causes a voltage drop, and it directly negatively impacts the characteristic and the stability of the electric arc. Leads to poor weld quality, inconsistency.
Absolutely. Poor connections are a common source of problems. And on the safety side, of course, it's non-negotiable. You must always confirm the current carrying capacity, the duty cycle of your equipment. Make sure you're not overloading it.
Don't want to burn it out.
Exactly. And importantly, ensure its electrical insulation is intact and undamaged. Check those cables. The necessity of using correct extraction systems. Well, it can't be overstated. Welding generates fumes and ozone, which can be harmful. Proper ventilation or fume extraction is vital for the welder's health.
Right. Protect yourself.
And maybe the most fundamental safety and quality measure. Always ensure that the welder performing the work is properly qualified for the specific welding procedure being used. They need the right training and certification.
Absolutely essential. Okay, so moving beyond conventional MIG-MAG for a moment, let's talk about a really significant evolution. Flux-Cored Arc Welding, or FCAW. This was apparently a real game changer, particularly starting in the mid-1980s. It greatly advanced the successful application of on-site semi-automatic welding.
It really did. FCAW truly enabled a much wider range of materials to be welded effectively, especially out in challenging field conditions where traditional MIG-MAG struggled.
So what's the core concept there? How does it differ?
Well, the core concept with FCAW is remarkably clever. Instead of a solid wire, the cored wire itself consists of a metal sheath, like a thin tube, containing a granular flux inside. This flux can contain all sorts of elements, similar to those normally found in the coating of MMA electrodes or stick rods, and that's precisely why the process has such an incredibly wide range of applications and material compatibility. You can tailor the flux chemistry.
Ah, so the magic is inside the wire. And here's where its biggest advantage over conventional MIG-MAG for fieldwork comes in, right? You mentioned gas-producing elements and compounds can actually be added directly to that flux within the wire.
Exactly. That's the key for many applications. This allows the process, specifically the self-shielded variants, to be completely independent of a separate external gas shield.
So no need for the gas cylinder and hose in those cases.
Correct. Which directly addresses that major limitation of conventional MIG-MAG welding in many outdoor or windy field applications where drafts can just blow away the shielding gas and ruin the weld. It's a truly ingenious solution for those challenging environments.
That makes a huge difference on a construction site, I imagine.
Oh, absolutely. And wire quality in FCAW is crucial because of that internal flux. Most wires are sealed very carefully, mechanically and hermetically, to protect the flux inside from moisture pickup. The effectiveness of the seam or joint on the wire itself is a key inspection point, because moisture can easily get absorbed into a damaged or poorly sealed seam, and that moisture can cause hydrogen cracking and other weld defects. You absolutely want to avoid that.
So you have to handle the wire carefully.
Very carefully. And when we talk about common wire types, you'll typically encounter a few main categories. There are rutile wires, known for good all-positional capabilities. Basic wires, also good for positional welding, and often a bit more tolerant of dirty or contaminated base material. Then you have metal cored wires. These generally provide higher deposition rates, higher productivity, and sometimes even offer excellent root run capabilities, good for pipe welding, for instance. And finally, the self-shielded wires we mentioned, which, as the name implies, require no external gas at all. They rely entirely on the flux inside for shielding and deoxidation.
Fascinating range. And here's an interesting note from the material science side I read. Unlike traditional MMA electrodes, the potential hydrogen levels and mechanical properties of welds made with rutile flux-cored wires can actually equal those of the more robust basic types. That wasn't always the case with stick electrodes.
That's a significant point, yeah.
Yeah.
The chemistry allows for it.
Plus, crucially, apparently baking of cored wires, if they get damp, is ineffective. It will not restore the condition of a contaminated flux, unlike some stick electrodes.
Correct. Once moisture gets into that flux, the damage is done. You can't reliably bake it out. Proper storage is key.
It's just another great example of how innovation solves real-world challenges, using clever material science and understanding the process limitations.
Yes.
So, wow, we've journeyed through the intricacies of MIG-MAG welding, from its fundamental process, the clever equipment ensuring consistency, and even this peek into how flux-cored variations solve specific real-world limitations. We've seen how that continuous wire feed, the sophisticated automation levels, and smart component design all work together to create incredibly strong, reliable welds very quickly.
Indeed. And we've explored that balance, haven't we? The high productivity measured against specific challenges like joint access or environmental factors like wind. It really highlights how every engineering solution involves this carefully considered set of advantages and limitations. Each variation is designed for specific applications, creating this dynamic landscape of choices for manufacturers and builders.
Exactly. So for you, the listener, whether you're maybe prepping for a meeting, getting up to speed on a new field, or maybe you're just insanely curious about how things are built, the takeaway is pretty clear. This isn't just about melting metal together. It's a dynamic interplay of engineering principles, precision equipment, and yeah, a dash of truly clever automation that makes so much of our modern world possible.
And thinking forward, it does raise an important question for the future, doesn't it? How will the ongoing advancements, things like new materials, robotics, maybe even artificial intelligence, influencing parameter control? How will these continue to redefine what's possible with arc welding? How will they keep pushing the boundaries of construction and manufacturing even further in the years to come?
That's definitely something to mull over as you go about your day. Thanks so much for joining us on this deep dive.